Hello everyone, welcome to this screencast covering section 3.2 out of your textbook. It is uncertainty in measurement. So we might ask ourselves, why the focus on uncertainty? I will have you know that scientists are absolutely obsessed with this problem of uncertainty, and it really stems back to the founding of the scientific method, of which you guys learned that Francis Bacon was the one who really was the founding father of the scientific method. Now, he didn't call it that in his day, but recollect that the whole institution of science, the reification of science as a practice, it came about 100 years after we had the Reformation. And the founding fathers of science, these early guys who occupied chairs with the Royal Academy or with the Royal Society, these guys were Puritans, Anglicans, and Catholics. And for a lot of these guys, including Francis Bacon, oh my gosh, Francis Bacon being foremost among them, they all recognized that the Adamic fall not only instilled in man this proclivity to just be full of sin, but it also really stupefied man. The fall made man stupid. As an example, Martin Luther believed that Adam could look out into the far reaches of space and that Adam had telescopic vision. And Adam could see way beyond the farthest stretches of what they thought was the universe, or the solar. They didn't call it a solar system at the time, but the far stretches of the universe. They believed that when God was presenting the animals to Adam, after he had created Adam and Adam was naming them, they imagined that Adam almost had X-ray vision, and Adam could look in on the animals and have an idea as to their natural history and how they moved, how they created ecological niches and spaces for themselves. And Adam named them according to this essence that he could see. And all of this was, of course, done because Adam was this brilliant, brilliant man. And what the fall did was the fall really made Adam and all those who followed absolutely stupid. So what these founding fathers of science were looking for, they were saying, okay, if we're going to observe the natural world, we need to observe it with as much objectivity as we possibly can. And what this is going to involve is you better make sure that if you're going to come up with a theory for something, you better make sure that you had put together an experiment, and that part of that experimental process is taking a lot of measurements and using sophisticated measurement devices. And because these devices are not perfect and they can't give you an exact number, then you better reflect that uncertainty in the values that you report. And this is where uncertainty in measurement comes into play. Now, let's talk about this. So you see that image down there that has 4 different targets on it, and it's going to characterize 2 terms that are going to have a characterization that's going to be a little bit different than the way you might use them in everyday vernacular. As an example, you guys all have an idea as to what accuracy and precision describe, but in the world of science, in the world of measurement, it's exactly the same usage as we would use every day. Accuracy is a measure of how close a measurement comes to a true or theoretical value. And precision is a measure of how close a series of measurements are to one another. Now let's take a look at those 4 targets down there. If you look at the leftmost one, it shows 3 arrows that are on the bullseye, and they're all very close to each other. So we would say that those 3 arrows, that target there, represents 3 measurements that are both accurate and precise. The second target reflects 3 arrows that are on the outside of that bullseye, and we would say that those 3 measurements they're pretty accurate because they're close to a theoretical value, but they're not precise because they're not close to one another. The third bullseye shows 3 arrows that are in that yellow region, all very close to one another, and we would say that those are precise because the 3 arrows are close to each other, but not accurate because none of them come close to the bullseye. And in the final picture, it shows 3 arrows, one almost on the red, one in the yellow, and one on the blue. And we would see that those 3 arrows, or measurements is what they're representing, are neither accurate nor precise. They're not even close to each other, and they're not even close to a theoretical value. Now, Let me explain something. If you have something like the first picture, both accurate and precise, then you are looking at your measurement techniques and the instrument that you used. You can, with confidence, say, yeah, they're pretty legit. They're pretty good. If you look at that second picture and you've got 3 arrows that are accurate but not precise, then it would call into question your methodology. And you might want to re-examine your methodology for taking these measurements. In the third picture, you see 3 arrows that are precise but not accurate. And in that case there, you have an instrument that probably needs some calibration. So your instrument is giving you consistent recordings, but they're consistently wrong. So maybe you didn't tear the scale before you weighed something. And in that last one, you have a real disaster. Your methodology is bad, and the instrument that you're using is probably pretty much garbage. So again, all of these 4 representations here kind of tell us a little bit of something about our technique and about the instruments that we are using to measure. And this last term is resolution. And what resolution characterizes is the ability of the tool to detect small changes in what it is measured. So if you have a pretty sophisticated tool, then like let's say you have a mass balance and it is able to detect, you weigh a fly on it. So you put a fly on your mass balance and it gives you a measurement of 1.002 grams. And you look at that and you go, oh man, that's pretty cool. And let's say that you pull a wing off that fly and you take the mass of that fly again. And if it says 1.001 grams, then you say, yeah, that's a pretty legitimate scale because it was able to measure the distance, the difference in mass of the fly with 2 wings versus having just 1 wing. So that's a pretty decent scale. So we would say that scale then is pretty high resolution. So one thing that you should know is that all measurements involve some degree of uncertainty, and our reporting, how we report our measurements, actually reflects that degree of uncertainty. And it is impossible to make a measurement of the exact true value of anything. The only time that we can give an exact true value of anything is when we are counting. As an example, in our classroom, there are exactly 7 students. There aren't 7.2439864 students. There's exactly 7. So we would never say that counted values are that there's no significant digits. We say that they're all certain sure digits whenever we're looking at counting something. But when we're measuring something, we don't ever have an exact true value. Significant digits are the meaningful digits in a measured quantity, not a counted quantity, but a measured quantity. And answers expressed mathematically whenever you're conducting research involving measured quantities should have no more significant digits than the starting measurement with the least number of significant digits. Now, I will explain to you exactly what that statement means. So you're going to be doing this laboratory, and the laboratory is significant figures and measurement, and I'll get into this laboratory in just a minute, but again, any measurement device, whether it's a ruler, a balance, a spectrometer, or a kitchen measuring cup, is limited in its, they say precision, I think the better term would have been tolerance, or resolution. The degree to which the instrument is subdivided into graduated lines will determine to what decimal place the measurement will be reported. When reporting measurements, we include all of the digits of which we are certain, and then we always estimate that final digit. So, as an example, if you are using the ruler, like you see below, we can state the value with accuracy to the whole unit's level. So that means that if we have some measurement that comes in between 1 and 2, we can with certainty say the measured value of this particular thing, let's say you're measuring the length of a fly, okay? You can say with certainty that fly is somewhere in between 1 and 2 centimeters long. So you would have to estimate the 10th decimal place of that. So you might say, oh, that fly looks like it's 1.0, it's exactly halfway between 1 and 2. So in this case, you would say the fly is 1.5 centimeters in length. And anyone reading your measurement would know that you estimated that 10th place. Okay, that is just understood. But let's say that you have this ruler here, and in this ruler we have a higher resolution. You're going to be probably put in a position where your measurements are going to be more accurate, certainly, and if you're skilled, they'll be more precise. And let's say again that you put this fly on top of this ruler, and we see that it's 1 point, and if you look at these little graduated lines there, you say, well, it's a pinch beyond, it's a hair beyond that 0.5. So you could say that my fly is 1.52 centimeters in length. So anyone reading this value of 1.52 would know that you had a ruler that actually gave you the 10th value place of a centimeter. So I hope that makes sense, and that you had to estimate the 100th place. So we're always estimating one place value beyond the graduated lines on the measuring device that we're using. So in using this ruler, we can state a measured value with accuracy to the 10th level. So we have that as a certainty to the 10th level, but we would then estimate the 100th decimal place of any measurement we would make. If, for example, we're bored and we want to measure the length of dead flies in a windowsill. So in this activity, you're going to see those two rulers that, like you just saw in the last slide, and also you're going to see these three geometric shapes. And in this activity, you're going to measure them, first of all, using the less accurate ruler. So you're going to use the ruler with just the centimeters marked off on it, and then you're going to use the second ruler to measure all of these things again. So after taking the measurements as indicated on your printout for this laboratory, you're then going to derive measurements for perimeter, circumference, and area. So you're going to take two sets of measurements on all three of these shapes. The first set is going to be with your really stupid ruler that only has units measured off. The second set of units are going to be with the ruler that has 10th place marked off. So you're going to need to remember these formulas. You have the area of a rectangle. This is on that handout, which is area equals length times width. You have the area of a triangle. Area equals 1/2 times base times height. And of course, the area of a circle. The area of a circle is pi times the radius squared. And then, of course, I'm sorry, here's a fourth measurement, the circumference of a circle, which is 2 pi r. So again, make sure when you're working with lab partners in this exercise, make sure that you get all the measurements first. And then you can always make all of your calculations after you guys get your measurements. But always in a laboratory, get your measurements first, and you can always do the calculations later. Collect your data first. Don't sit there and fill out things on your laboratory that are not really, that don't involve collecting data. Because you may find in a lab that you run at a time, and you're going to have to leave. So every measurement then has some degree of uncertainty, as you will learn in this lab. It is important when reporting any of your data that you reflect that uncertainty, and that is exactly what significant figures accomplishes. So here are some rules for determining whether a number is significant, and they are as follows. Whenever you look at a measurement, all non-zero digits are significant. Any digits in a value that are non-zero are always significant. If you have zeros between non-zero digits, they are significant. For example, you see the value 304. Well, that zero there is significant, so you would say that this first number, 304, has 3 significant figures. That second value, 26,007, you have zeros there that are in effect acting as placeholders. So you would say 1, 2, 3, 4. There's 5 significant figures in that second value. And then in this third value, you have 0.62005. Well, look at the zeros that are in between non-zero digits. So this first zero here before the decimal, that is not significant. It's just a placeholder. But the zeros in between the 2 and the 5 are significant. So you would say that this has 1, 2, 3, 4, 5 significant digits. So in numbers with a decimal point, beginning with the first non-zero digit, that is 1 through 9, all numbers including zeros to the right are significant. So if you look at this value here, you have 310.00. So we would say that this has 1, 2, 3, 4, 5 significant digits. Okay? So, and we include these as significant because they are right of the decimal point. Okay? Then we see 4.330. There's 1, 2, 3, 4 significant digits. And again, because that 0 is right of that decimal point. Okay? On the other hand, the zeros in this number here, you see this number here, 0.000324 and 0.579. The zeros in these numbers are not significant. They are important because they hold a place, but they are not considered significant. So again, if you look at this first number, 0.000324, well, if I were to write this in scientific notation, it would be 3.24 times 10 to the negative 1, 2, 3, 10 to the negative 4. And there's no significant, none of those zeros are significant there. Again, these are just placeholders. These up here are not acting in 310.00. That's not a placeholder. Those zeros are not placeholders there. Okay, those are actual measured values. Okay, in numbers without a decimal point, just trailing zeros, those to the right of the last non-zero digit are not significant. And as an example, compare these two numbers. I have 310 and 4800. In both of these cases, 310 and 4800, I would say those zeros are not significant. So in 310, I have 2 significant figures. And that 0 is an estimated digit. In 4800, I have 2 significant figures with the 2 zeros estimated. But if you look at 310.00 and 4800 with a decimal there, I would say that all these zeros are significant. And that's because these zeros are not placeholders, but these zeros are the consequence. You see the 4800 with the decimal there? What that tells me is that that actually was a measurement up to that unit's place. Okay, but if you look at just 4800 without the decimal point, those last 2 zeros there are merely placeholders, and the 2 zeros reflect an estimate. Okay, so this is where students get really confused in significant digits, is how to deal with these nasty zeros. When is the 0 acting as a legitimate measurement, and when is that 0 just being a placeholder? Now I just have to tell you that be patient. The more you work with significant digits, the more the logic of significant digits will really make sense to you. So here's some exercises that we can work on here. Indicate how many significant figures are in each of the measured values that you see there. So in that first value, 246.32, how many significant digits? Well, there's no zeros in that one. That one's easy. There's 5 there. In that second number, 107.854, you say, oh, wow, this is really easy because that 0 is between 2 non-zero numbers, so that 0 is significant. So in that second value, there's 6 significant digits. If I look at this third value, oh, wow, I have zeros in between 2 non-zero numbers, so those 2 zeros are significant. I have 4 significant figures there. In this fourth value here, 0.678, oh, holy mackerel, well, that 0 is not between 2 non-zero numbers. It looks like that 0 is merely a placeholder. So I would estimate that there's 3 significant digits in that one. In the fifth value, 1.008, again, it's easy. When zeros are in between non-zero numbers, we always say those zeros are significant. So there's 4 significant digits there. But what of this last value? We have several zeros there, and none of them are in between non-zero numbers. So I'm going to argue that these first 3, at the very least, are placeholders. And that last one I'm going to say is significant, so we would have 3 significant figures in that last value. So now that we have identified significant figures, we have figured out how to look at a value and count the significant digits in it, or the significant figures. This all comes into play when we're reporting data and when we are adding measurements, subtracting measurements, multiplying or dividing them. There are some calculation rules that you need to keep into mind. Whenever you're adding or subtracting, the answer must be rounded to the place which has the greatest uncertainty. Okay, and I'll explain this in just a minute. When multiplying or dividing, the answer must be rounded to the same number of significant figures as the factor having the smallest number of significant figures. And you're saying, what in the world are you talking about, Mrs. Morales? Well, let's solve some problems here. So these are adding and subtracting calculation rules. Let's remind us of those rules. When adding or subtracting, the answer must be rounded to the place which has the place value, which has the greatest uncertainty. So in this first problem here, 32.567 plus 135.0 plus 1.4567. If we look at those 3 numbers there, each one of them has a different resolution. So we see that this last value, the third, the bottommost number, has the highest resolution because we're going into the, let me see, tenths, hundredths, thousandths, 10,000ths. Yeah, this one goes to the 10,000th place, whereas this middle number only goes to the 10th place. Well, when you calculate that final number, that's going to be the value that you're going to get. You're going to have to round that off so that your final value reflects the lowest resolution of the 3 numbers that you're adding in this case. So in that case, you would round this off to 169.0. Okay? And doggone it, didn't mean to do that. We have 3 numbers here that we're adding up. And if we look at them again, if we add all these up like we see it, we get this value. But because this third number here only goes over to the 10th place, when you report this number, you're going to have to only report it to the 10th place. So that's pretty easy. 582.8 would be the final number that you would report. And then this one here, again, the lowest resolution number is the top number, which only gives us a value to the 10th place. So we're going to add all of those up, keeping as many digits as we can. So don't dodge your digits until the very end. Wow, that almost sounded like it was a poem. So in this case here, we have this final value here, but when we report this in our lab, on our exam, in a scientific paper scientific research, we are going to round this off to the units place. So it would be 2026.8. So here again, these values reflect that rounding off. Okay? And we had already discussed all these values. Okay? So don't dodge all these other numbers. Don't count these long strings of numbers as superfluous or unimportant. Keep those numbers and do your rounding off for significant figures purposes at the very last. When you've done the calculation, then round it off. Okay, so these rounded values represent the limitations of our measuring instruments, be it a ruler, thermometer, graduated cylinder, mass scale, whatever. That's what these things all reflect. Multiplication and division calculation rules. When multiplying or dividing, I will say that I think that the rules here are a little bit easier. The answer must be rounded to the same number of significant figures as the factor having the smallest number of significant figures. So we have this here, 23.7 times 3.8. Well, I see 3 sig figs here on 23.7 and only 2 sig figs on 3.8. So when I get that final value for that top problem, I'm going to reflect only 2 significant figures. In this bottom one, in the second one here, again, the factor that has the less number of significant figures is 64.1, only 3 significant figures. Here I have a division problem. So this number here, 3.74, has only 3 significant figures. I'm going to make sure I reflect 3 significant figures in that answer. And here we have 4 significant figures divided by 4 significant figures. So here's the calculations as I will perform them on my calculator. Remember, I said don't ditch any numbers until you're getting ready to report your final number. Okay, so here's how they are calculated, and oops, here's how, sorry about that, my order of slides got all messed up. And here is how they're going to look. So this top one, 2 significant figures. I'm going to reflect a value with 2 significant figures. Know that I did not just say 90, but I said 90 point. Because if I just wrote 90, that's a value representing 1 significant figure. But 90 point shows 2 significant figures. Okay, that little decimal says that I actually did this calculation and I got 90 point something. Okay, and then of course here I have 3 significant figures, and both of these values, 2,780 is definitely 3 significant figures, or if I write it in scientific notation is 2.78 times 10 to the third, that's also 3 significant figures. So either one of these will work. On this third calculation, 3 significant figures, and on this fourth one, 4 significant figures. Okay, so I could report them either way. Okay, hope that makes sense. So whenever you are reporting any final data, such as an answer in an examination or quiz, you need to report the answer so that it reflects the proper number of significant digits. So like I said, I'll be a little easy on you initially. Excuse me. I'll be a little easy on you initially, but over time I actually will start docking points probably after your first exam for not using significant digits. So I already said this, I realize I am beating a dead horse, but do not round off digits until you report the final